All right, welcome. If you're here to conquer the electrical technician exam, you are in the right place. We're going to break down some classic problems, but here's the twist. We're not just hunting for answers. Nope, we're digging into the why behind them, the core principles. Okay, let's get right into it.
Look, I get it. It's so tempting to just memorize the answers, right? But trust me, if you want to really nail this exam, you've got to go deeper. Our goal today? Ditch the memorization. We're going to build a real gut-level understanding so you can tackle any question they throw your way.
So first up, we're going to kick things off with a big one, magnetism. We'll group a bunch of questions that all deal with that invisible but super powerful force, and induction. This is the bedrock, the foundation of so much, so we got to make sure we have it locked down tight.
Okay, this first one, it's a total classic. You're almost guaranteed to see a version of this on the exam. It's all about the magnetic field you get inside a toroid, that donut shape. And the secret to solving it? It all comes down to one key formula.
And here's the formula. Just look at how simple the relationship is. The field strength, that's H, it's directly tied to the current, I, and the number of turns in the coil, N. So, more turns or more juice, you get a stronger field. Makes sense, right? And then, on the flip side, it's inversely proportional to the radius, R. So the bigger that donut gets, the weaker the field is. It's really that straightforward.
All right, next up, let's think about what happens when we actually use these magnetic fields in the real world. Every time you magnetize and then demagnetize a material, like over and over again, you actually lose a little bit of energy as heat. It's like friction, but for magnets. This is called hysteresis loss, and oh man, the exam loves to see if you know what affects it.
So here's what you absolutely have to remember. The loss goes up with frequency. That just makes sense, right? The faster you flip that magnetic field back and forth, the more heat you're going to generate. But here's the magic number, the detail the examiners are looking for. The loss is proportional to the max flux density raised to the power of 1.6. That is such a specific number. It's not 1, it's not 2, it's 1.6. Burn that number into your brain.
Now this next question, this gets right to the heart of how we generate electricity. I'm talking generators, transformers, the whole deal. It's all about Faraday's law of induction. And what's that? It's the amazing principle that if you have a changing magnetic field, you can actually create a voltage in a coil of wire. It's basically magic.
And check it out. Once you know the formula, the math is pretty simple. The voltage you get, that's E, is just the number of turns, N, multiplied by how fast the magnetic flux is changing. So let's plug in the numbers. We've got 150 turns, a 1 Weber change, happening over 2 seconds. Boom! That gives us 75 volts. And hey, you might see a negative sign in the full formula. That just tells you about the direction of the current, but for a question just asking for voltage, 75 is our magic number.
This right here, this is the definition of a Henry, the unit for inductance. It's a direct link between how fast the current is changing and the voltage it creates in itself. I love the analogy that inductance is like electrical inertia. It hates change, it pushes back, and that idea is a perfect bridge into our next section.
Okay, part 2. We're going to build on that foundation. We're shifting gears a bit, moving from the deep physics of magnetism to the practical, nuts and bolts, rules of the road for circuit analysis. Think of these as your toolkit for breaking down really complex circuits and making them simple.
All right, here's a situation you'll definitely see, especially with three-phase power. The exam writers love, and I mean love, to test if you can simplify a circuit by converting a delta connection, that's the triangle one, into its Y equivalent, the star-shaped one. And the best part? The math is beautifully simple. To go from delta to Y, you just divide by 3. The impedance in the Y circuit is exactly 1/3 of the delta impedance. That's it. Just remember, Y is the little guy. It's smaller than delta by a factor of 3. That's all you need to know.
Okay, take a deep breath. I know this circuit looks like a mess, right? It seems super intimidating, but here's the secret. It's not about complex math, it's about spotting a pattern. This specific layout is called a Wheatstone bridge, and once you see that, this whole problem just unlocks. It gets so much easier.
And here is the magic trick. The key to the Wheatstone bridge is balance. See how the resistor ratios on the left and right sides are the same? That means the bridge is balanced. And when it's balanced, get this. 0 current flows through that resistor in the middle. None. Zilch. So for our calculation, we can just, poof, pretend it doesn't even exist.
So with that middle resistor gone, this thing becomes a piece of cake. Looking at points A and B, we've just got 2 parallel branches of 2R each. The total resistance there works out to just R. Now look at C and D. That's 3 resistors in parallel. And when you do the math, it comes out to R over 2. So what's the answer? The resistance from A to B is exactly double the resistance from C to D.
You know, whenever you have an inductor in a circuit, it kind of messes with the timing. The current always falls a little bit behind the voltage. It lags. And the phase angle, that little theta symbol, tells us exactly how much it's lagging. This formula shows it's all about the battle between the inductor's reactance and the circuit's resistance. It's like a tug-of-war between those two properties.
All right, let's bring it home. For our final part, we're getting to the main event, the electricity itself. What is this stuff? How do we measure it? And how do we talk about the different kinds of power it gives us? Let's dive in. Okay, a super simple question on the surface, but it's really asking about the most basic thing of all. What is electricity? I mean, what is the actual particle that's zipping through the wires to power everything?
And the answer is the free electron. That's it. In a conductor, you've got these electrons on the outer shells of atoms that aren't really tied down. They can just get up and move, carrying their charge with them. And that massive flow of tiny little electrons, that's what we call electric current.
Here's another classic exam topic, telling the difference between the types of power. Let's talk about reactive power. Think of it like the foam on a beer. It's there, it takes up space in the mug, but you can't drink it. It's the power that just sloshes back and forth in the system, building magnetic fields, but not doing any real work, like turning a motor. We measure it in VARs, and the key thing to remember is that its formula uses the sine of the phase angle. The cosine is for the good stuff, the active power.
Whoa. Okay, here's another one that looks absolutely terrifying, right? But just like the Wheatstone bridge, it's all about knowing the rule. What you're looking at is a messy, complex current. It's got a DC part and then a couple of different AC frequencies mixed in. To find its true effective value, what we call the RMS value, you can't just add the numbers together. There's a special trick.
And the rule is actually pretty cool. It's the square root of the sum of the squares. Sounds complicated, but it's not. First, you take the DC part, that's the 3, and you square it. Then you take the RMS values of the AC parts. Now remember, the formula gives us the peak values, so we just take the numbers in front of the sign, which are 10 and 5, and we square those. Then you just add them all up and take the square root of that final number.
And when you punch that into a calculator, you get 11.6 amps. And that's not just a theoretical number. If you took a true RMS multimeter and measured this weird current, that is the value you would actually see.
Man, we have covered a ton of ground. We went from magnetism and induction all the way to circuit analysis and power. So to wrap it all up, let's put all the key formulas we talked about onto one final slide. This is your cheat sheet. And there you have it, everything in one spot. Seriously, this is a good time to hit pause, maybe grab a screenshot or just jot these down. Think of this as your quick reference guide. But don't just see them as formulas, right? Each one tells a little story about how electricity works. Use this to really make these concepts stick. Because at the end of the day, that's the whole point, isn't it? These formulas aren't just hoops to jump through for an exam. They're the language of electricity. They're the tools you use to understand how this stuff really works. When you see the patterns, when you get the principles, you're not just studying for a test. You're on your way to becoming a fantastic technician. So the real question is, now that you see the connections, where are you going to start?